Hello, everyone. My name is Blair Schneider, and I am the past chair now of the SEG Women's Network Committee. And this year, I've taken over the role of scheduling our webinar sessions. And I am so excited to introduce Esther Babcock today for you. She earned her master's in environmental science from the University of Arizona and her PhD in geophysics from Boise State University. Prior to graduate school, she served in the Air Force as an officer and pilot, including 62 combat missions. After her military service, her geophysical work is focused on near-surface investigations for geotechnical and environmental applications. Her geophysical field experience spans the globe from Alaska to Africa, from Antarctica to Canada, and she currently owns and operates Logic Geophysics and Analytics, which is based in Anchorage, Alaska, and conducts projects across the state. So I will now turn it over to you, Dr. Babcock.
Thanks, Blair. Just to make sure you can hear me, right?
Yes.
Okay. Yeah, thanks for the introduction. Good morning, everyone. Thanks for coming to my talk. I feel incredibly blessed to live and work in Alaska, and I'm very excited to share some of the different experiences I've had in the state with you here today. Hang on one second, that does not seem to work. There we go. So where are we? This is a polar projection map showing Alaska and the 7 other nations besides the United States that make up the nations with presence in the Arctic. And here I am talking to you today from Anchorage. Many of you, or some of you listening might be from Alaska, but I know many of you aren't. So I'm going to start with a little bit of an overview about the state. First of all, Alaska is enormous. It's kind of hard to comprehend exactly how big when I can jump in a plane and take a nap and wake up 500 or 600 miles away. But that does come home a little bit more when you're working out on the tundra in the swampy lakes and streams, and you realize it would take you a very, very long time to walk just about anywhere if you didn't have, modern resources. I've also been in the unfortunate position of watching an aircraft in a village take off without me. That was supposed to be my ride home. That also makes your remoteness hit home very quickly. Alaska is a very diverse place, of course. We have mountains and glaciers, rivers and beaches, rainforests in the southeast, and lots of tundra that is really hard to walk on sometimes. Long days and nights, and some projects happen during the night, as we'll talk about. And then, of course, villages and towns with what might be considered more standard infrastructure. As I mentioned, it's a very large state. Many of you might be oil and gas professionals and familiar with Prudhoe Bay and the oil and gas fields on the North Slope. I recently learned that the first commercial oil well was in southern Alaska, where that red star is, in 1902. So that's pretty interesting. There's also a lot of mining in the state. We have world-class resources of gold, silver, copper. Red Dog mine in northern Alaska, just that one mine produces 10% of the world's zinc. So there's a lot of mining applications for geophysics. And then there's engineering and environmental applications as well. We don't have a lot of infrastructure, maybe, compared to the lower 48. And you can see the road system there is pretty limited compared to the size of the state. But nonetheless, there is infrastructure that geophysics can be applied to, especially after the earthquake in 2018. For example. And then unfortunately, there are many contaminated sites throughout the state, whether that's associated with unexploded ordnance from military activity or old placer mines or just trash and debris that was left during old highway constructions. But a lot of those contaminated sites can have geophysics applied to them as well. I'll have you just note the road system again and compare that to the many villages and towns that are strewn throughout the state. So most of these settlements do not have road access. So access is either by aircraft or in the wintertime snow machine or boat, as some of these coastal villages get a lot of their services that way. And that will come up during this talk more. Oops, sorry. So I thought today that I'd talk about 5 different case studies, each associated with a particular geophysical method. And you can see those listed here. So we will start with ground penetrating radar. I'm going to give a high-level broad brush overview of each method for anyone who might not be familiar with it. I know as geophysicists, sometimes we tend to get pretty specialized in our own little niche world. That's one of the things things that I like about near surface geophysics is how much variety there is. So ground penetrating radar, just like it sounds, is using radar to image the ground. So we introduce electromagnetic energy that travels as a wave in the right conditions and reflects where there are changes in electrical properties back to a receiver where we can measure it. There are other ways to employ this, such as the diagram on the right showing cross-borehole GPR measurements. There's a wide range of applications for GPR, and I have them listed here kind of from simplest to most complicated. So there's a lot of ways you can define simpler or more complicated, but concrete imaging, for example, often we're looking for rebar in concrete, which is a very high electrical contrast. So those targets tend to stand out very well. Whereas imaging contaminated sites, for example, at the bottom of the list, where we might be looking for a contaminant that has low electrical contrast relative to the groundwater, for example. And so there might be a chance we can't detect that with the radar. Another interesting thing about GPR is that the instrumentation is quite variable. I'll show a few pictures to explain what I mean in size and in characteristics. I will note here that this instrumentation is very sensitive. This whole sampling in picoseconds and time window in nanoseconds. I can't honestly comprehend what a nanosecond is, even though I've been working with GPR for many years, let alone a picosecond. So it's pretty fascinating and amazing to me that I can take a transmitter and receiver that are that sensitive and bump them along the tundra on the back of a snow machine for 4 or 5 hours and then take them out and they still work. So I'm very appreciative of the electrical engineers that figure that out. So I'll show you 3 different systems here. This is a concrete imaging system. Note that it just spits in the palm of my hand. This is a 100 megahertz system. So see the size difference, and what I'm trying to get across is the variability in the systems. And then on the left, a 25 megahertz system with about 4 meter long antennas. I've also highlighted this person in the background here. So this is my friendly bear guard. We'll talk about this on at least one other project, but many of the sites where I go, there are black bears and or brown bears and or polar bears. And so often I'm accompanied by a bear guard who's trained and armed and competent and keeps an eye out to make sure that I don't get eaten, I guess. All right, so with that being said, the first case study we'll talk about is the GPR case study. It's located in Wainwright, Alaska, which is where that red star is, about 700 miles away, direct line from Anchorage. Here's a few pictures. The bottom picture is a picture I took during the project, and this is about as light as it got outside during the day. This was a December project, so the sun never actually rose during the day, but we did get a couple hours, I don't remember exactly how much, a couple hours of light to work in, and the rest of the time, darkness. We were looking for underground utilities at this project in support of an infrastructure project. And the logistics was a flight from Anchorage to Wainwright, a direct charter flight. On the way back, I've shown 2 different paths. We chartered a flight to another town that has regular air service back to Anchorage, save a little money. Lodging was a construction camp. I like camp life. Camps have take all different kind of flavors and looks in Alaska. I won't try to describe that here, but sometimes, many times it's connexes that have been repurposed into camps. And then HSE for this project was cold weather and darkness. So we were working down to about -20 Fahrenheit, -15, -20 Fahrenheit. It's about -25 Celsius with winds of 15 to 20 miles an hour. That gets cold really quickly. So we're trying to keep the humans and the equipment warm. And then it was dark out for most of the time that we were collecting data. So just even from a simple slip and trip hazard, dealing with a snowy surface in the dark can really be an HSE concern. We'll take a side note here to talk just about some unique HSE challenges in Alaska. I have a list here for you. We're working in remote sites, and there's oftentimes wildlife around or in the area. I have been, I won't say chased, I have removed myself from more than one project site due to a bear wandering into the project site. At one of those times, our egress plan took us out of sight of the project area, and everyone was safe, but I spent the 10 or 15 minutes we were hunkered down thinking, please don't eat my equipment, please don't eat my equipment. So anyway. Then we have a whole host of combinations of different weather conditions, so cold and heat. I've gone from stopping work because of frostbite concerns to a couple weeks later, asking a neighbor in a house near the project if I could borrow their hose to hose myself off because I was very hot. I do get hot easily, for the record. So that definitely makes field work challenging and interesting, in my opinion. And then travel. I'll talk about that a little bit more later, so I won't belabor the point here. And of course, all the standard HSE concerns apply on these projects, slips and falls, especially when working on the tundra, which can be very uneven, soft ground and difficult to walk on. For this project, I used 2 different frequencies of antennas. I'll show a picture of the other frequency in the next slide. Here on the lower right, you see the 500 megahertz setup on a wheeled cart with gridded acquisition as we were trying to locate utilities, and we didn't have a very clear idea of which direction those utilities might be running ahead of time. The project was pretty successful. Very successful. We found 40 potential obstructions, likely utilities, that were marked on the ground, and there was a drilling campaign going on at the same time, and we completed all that successfully with no safety incidents. Here's a picture, as I was saying, on the lower right of the different frequency. This is 200 megahertz frequency. So you can see a little bit that it's a little bit bigger than the 500 megahertz and travels a little less easily over the frozen or snowy ground. This project was great because the site was well plowed beforehand, but that's not always the case, as you can imagine. And finally, I'll show a data example. So on the top figure, you can see the GPR data where the hyperbolas are oftentimes associated with the presence of a utility. And so that was the case here. Very good data and easy to image the utilities. And on the bottom, from a plan view, so we collect the data in a grid and then we can process those data in a plan map view. And that helps draw your eye to coherent anomalies that might be more likely to be associated with the utility or obstruction of concern. This particular anomaly I'm showing was a large diameter pipeline that we were able to avoid. So that is GPR. The next method I'll talk about is seismic. I'm going to assume that most of you, or many of the geophysicists anyway, listening are most familiar with seismic. So again, I won't belabor the point. In the near surface realm, we use several different methods I have listed here: reflection, refraction, MASW, and borehole seismic. Oftentimes we're using an active energy source, but I have usually starred there because we can do passive acquisition as well. And MASW, I'll say, is becoming more and more popular because we're using a surface wave, which have a lot more energy of the signal in them than reflected or refracted waves. So that promotes a high signal to noise ratio and is more tolerant of noisy environments. Seismic instrumentation, again, many of you familiar. Geophones, cables, and a source associated or accompanying hardware and software. Common sources that I use are sledgehammer and Betsy gun. That's the most common for me. On the left, you can see the Betsy gun on a site in Alaska, and on the right, of course, the ubiquitous sledgehammer. There's a move in the near surface realm to cable-less systems, but there are drawbacks to nodal systems and advantages. I've just recently purchased a system called Summit X1, which uses a 2-wire telemetry cable instead of a traditional seismic cable, with the A to D conversion happening at the geophones. And I think that's a significant advancement in terms of acquisition and kind of bridges the divide between nodal and cable systems. Here's a picture of the setup. Note the UTV in the background that got us to this site, so we didn't have to lug all our gear in through the woods ourselves. Technology is handy. So this next case study, a seismic case study, is located in Metlakatla. This is a little village on an island in southeast Alaska, pretty much as far south as you can get in Alaska. The target here was, I think I skipped the, yeah, I meant to leave the pictures. Oh, and I'll make a note about the pictures as well. This is what I like to call tourist pictures. So this is a very rainy place. This is where some of the rainforests in Alaska are located. And these pictures, I would say, are atypical, but no one would want to take a cruise ship to that island if you just showed the rainy pictures. The target here was depth to bedrock. Logistics were a commercial flight. I didn't break it up in the arrow, but a commercial flight on Alaska Airlines to Ketchikan, and then a ferry, a car ferry to Annette Island. So that's not so bad. Anytime I can take a regular commercial flight to a town instead of a charter or one of the other smaller airlines, I feel a little bit better that I and all my equipment will actually get there and back at roughly the same time. There's a hotel on this island, so that's delightful, change from the usual camps. And then the biggest HSE here was traveling even that far south. It was quite squishy tundra with small vegetation, very easy to trip walking in this environment, even if you weren't carrying anything, but then we're lugging gear around. So that was my biggest concern. I'll take a side note here and revisit the logistics piece. It's interesting to me how much time I spend on the various different tasks, but they're all equally important. So I spend a lot of time planning and getting logistics in order, making sure I have all the equipment, taking spare tools. Oftentimes I'm in a place where there is either no store or very small store where if you don't have a tool you need, then your project might be shot. I take a soldering kit everywhere I go. That saved me more than once for soldering connectors or wires together to make equipment work that somehow got damaged. And also, I think I'll say this again, but forgetting things is expensive. So if you're taking a $7,000 charter flight to a village each way and you forget something, if that's the only way in and out, then getting another one of whatever you've forgotten is $7,000. So that's an expensive mistake. But then even with all the time that's spent making sure we can get there and get back and actually carry out the data collection plan properly, all these other parts of the geophysical survey can't be left behind. So you need every single one of these to be successful in order for the project to be successful. I just find it interesting how the time is split between these different tasks. All right, so back to the project. I have a little bit about the equipment here. One of the problems with seismic data acquisition in Alaska is that we're dealing with this spongy vegetated surface layer that you do not have coupling with a geophone or your source if you're just pushing things into this loose material on the surface. So you have to get down to the actual soil, which can be 1 or 2 or 3 feet below the actual surface. So you can auger down to that. You can cut out clumps of the tundra and pull it out. You can use extenders on the geophones. You can see I've circled the geophone there to highlight it since it's hard to tell from the picture, but it's buried down in a hole that I dug to get the geophone down in there. And same for the sledgehammer, you need to get that sledgehammer plate down on the actual material. This is where the gun that I mentioned is pretty handy because we auger out a hole for that and put the barrel of that, or muzzle of that gun, sorry, in the hole. So that's 2 to 3 feet below surface. So you're going to have good coupling right from the get-go with that. And here's a picture of the collected data. So this was a refraction survey. So we're showing P wave velocity. There was a borehole to ground truth. The results and the competent bedrock surface was interpreted as being associated with what I have here is colored in red. So about the 8,000 foot per second. From that borehole information. Next method is resistivity. So electrical resistivity surveys work to discriminate targets based on contrast in resistivity / conductivity. The reason why this interests us is that resistivity is often related to a host of properties of the material that we might actually be interested in investigating. For example, mineral content, pore fluid, variations in permafrost, mass ice or thaw bulbs in the permafrost, mapping contaminated zones where there's a difference in conductivity between the contaminant and the groundwater. So there's a wide range of applications for this method as well, both from an exploration geophysical perspective to an environmental perspective. In a resistivity survey, we inject current between 2 electrodes, and then we measure the potential difference across 2 other electrodes. We do that in a line of these electrodes in different configurations and spacings, and the line of electrodes can be 14 to over 100 or maybe even more. So you can get really long lines, which increases your depth of investigation. Here's a summary again of the applications, just showing different targets. So bedrock could be a target for these surveys, just as bedrock can be a target for seismic surveys. So which tool you want to use, I spend a lot of time thinking about, which tool is the best for the given scenario with the knowledge I have about the site conditions beforehand. I've heard that people do site visits, but in Alaska, that's almost impossible. I think I've only done 2 site visits out of all the projects I've done beforehand, because getting there is very expensive and takes a lot of time usually. So most of the time we're relying on information that somebody else has told us, or a previous project, or somebody else who may have gone out to the site to get any information about what we might be dealing with. For the instrumentation for this particular method, our source is essentially an electrical source, so a battery or a generator to allow this current injection and to run the associated electronics. We push an electrode into the surface, you can see circled here, at each position with whatever spacing that we've decided to use for that survey based on our survey design and in our planning, and then those are connected with a cable. So kind of similar to seismic, how you have cables running down the line and instruments at specific spacings. All right, so resistivity case study number 3 was located in a place called North Pole, Alaska. Yes, there is actually a town named that. I used to live there for a couple of years. It's a delightful place. There is the obligatory tourist trap where you can go at any time of year to get your Santa Claus trinkets. I'm not a Christmas person, but I was forced to go inside there one time. This is close to Fairbanks, which is the second, 30,000 people thereabouts, the second largest city in Alaska behind Anchorage. So there are resources here, but still, one does not want to forget anything. The target here was locating gravel resources and delineating permafrost conditions. This town is actually on the road system, so you can drive to Fairbanks and then a little bit south to North Pole, or you can take about a 1-hour commercial flight between Anchorage and Fairbanks and then rent a car and go to the project site. Another hotel for lodging. This was actually a full-blown commercial hotel. Maybe I didn't mention it, but the hotel on Annette Island is, a small tourist hotel on a tiny island or a small island. So this was kind of a step up in accommodations maybe. And then as far as HSE concerns, it was pretty hot sometimes on the project site. My version of hot might be different than yours, but it's still a concern. And we were working in an area where there could be bears, which is most of Alaska. And so there's a group of us, so make a lot of noise. We didn't have a bear guard on this particular project due to the fact that we didn't think it was as high a hazard that would warrant that. And then I think bugs fall into wildlife as well. So we were working in an area where the bugs were pretty horrendous at times. I already talked about that. But I did want to talk about logistics a little bit. So it's kind of another side note in my segue of side notes. So there's a lot of different ways to get to projects up here in Alaska. The variety is pretty interesting. Everything from skis to, get there or use on a project. Skis, snow machines, planes landing on glaciers, helicopters, souped up 4-wheel drive vehicles to try to get through almost impassable roads, normal ATVs to make your life easier. And then on the upper right, there's a landing craft that I was on for one project. So It's pretty interesting, all the different ways to get around to projects here. I haven't yet taken a train or a dog sled on or to a project, so I'm waiting to add those to the list. All right, back to this particular survey, we used the SuperSting instrumentation with lines of 56 electrodes at 10-foot spacing. And then the setup time was pretty quick. We had a crew of 4 and everyone was working really well together. One of the problems we ran into is that this was a gravel investigation, and some of these places actually had gravel, coarse grain gravel right to the surface. So there were high contact resistances encountered, and I'll show a picture of us watering the electrodes. I'm sure some of you are familiar with that process. We also combined this particular work with low frequency GPR surveys and a drilling campaign that was going on at the same time. So there was 2 different types of geophysics that I used on this project. I will talk for a second about positioning the data. So these data we were positioning to survey grade quality. I've heard, although I haven't done a lot of work in the lower 48, I've heard that in the lower 48 you can get subscription-based GPS satellite services and operate with not quite survey grade quality maybe, but less sub-foot accuracy in many places. Many of those subscriptions do not cover, most of those subscriptions do not cover Alaska and the places that I'm doing projects. So oftentimes the only way to get survey grade data is to use a base station and set up or have a known control point. So the trade-off is between the extra work and time and cost of getting survey quality data using this process or having very low quality GPS, so 5 or 6 foot accuracy. We don't really have an in-between in many cases up here. 2 different pictures of the site conditions to show you how variable even one project can be. So on the right, here's a picture of the crew watering the electrodes to try to drive those contact resistances down. And then on the left, marshy, trying to keep your feet dry, walking along, and the equipment dry, walking along this marshy area, which of course is where all the mosquitoes are. So that makes things a little bit less pleasant, perhaps. Oh, and I will say, these were the sunny days during the projects. We had, it was either 2 or 3 days in a row that were the 2 or 3 highest cumulative rain days that Fairbanks had ever had up to that point. That was great. Here's a picture of the data results. So on the top figure, this shows the clear differentiation of the permafrost of the frozen materials on the right with very, very high resistivities from the thawed materials on the left. And we correlated on the bottom figure, all the materials were thawed. There wasn't any permafrost in that particular line. So we were able to differentiate the thawed regions from the frozen regions for the project, which was quite a success. And then also we were able to correlate gravel deposits from the borehole data with resistivity values. In this case, in the lower figure, the resistivities of gravel were around 1,000 ohm meters associated with that green color that I have, the lighter green color. It was really great to have both the GPR and the resistivity and the borehole data on this project to be able to correlate results between all 3 of those methods. All right, I'm calling this method 3A, so capacitively coupled resistivity. In this method, we drag an array across the ground instead of pushing stainless steel electrodes into the ground. You might imagine this can make acquisition much quicker. It mimics a dipole-dipole configuration, but on smooth ground, we can collect miles per day instead of thousands of feet per day that you might get in a resistivity survey. However, we are depth limited with this method due to the maximum length of the arrays. So that's a consideration. And also you're restricted to a smooth surface. Thankfully in Alaska, we have lots of smooth surfaces when it snows outside. So on the snow-covered tundra, this is a great environment for using this particular tool. This is the Geometrics Ohm Mapper here. You can see the tracked vehicle that we're using to pull it across the tundra in this array. The arrays can be one transmitter with single receiver or multiple receivers. And on the right, you can see I have multiple receivers here lined up behind the vehicle. And it can be towed, you know, not just with a giant tracked vehicle, but I've pulled it myself. I've pulled it with a regular vehicle if you're collecting data on asphalt with this particular tool, for example. And then positioning is provided by differential GPS, which was good enough quality up here on the in the north. This is on the northern slope of Alaska. The tool can get a little bit finicky in the cold. I'll define that here as less than -20 Fahrenheit. But in fairness, I get a little finicky in the cold at that temperature too. So I think it works really, really well given the conditions that I've exposed it to. I wanted to show this picture because you can see on the right, there's very little contrast, if you'll note, between the sky and the ground. So oftentimes on the slope, I've run into these conditions where you can't, it's like you're driving into pea soup. You can't really tell what's in front of you. After about an hour, I get a really bad headache because you're just kind of squinting and trying to see any contrast that you can, and there's no contrast whatsoever, which is also a concern from a navigation perspective if you haven't traveled that route before. So for one of these projects, we went to collecting data at night for a different reason than this pea soup problem, but it turned out really, really well. So on the left, I have a picture of data collection at night of the array strung out behind the vehicle. Eliminates that problem with, you know, not being able to really differentiate between ground and sky. Turns out you can also, I did not really think about this, see a headlamp from about 3 miles away on flat ground if there's absolutely no other lighting. So it's a good, we were able to set up references to guide us and to point to on the tundra. Yeah, and also during this project, this was wintertime and we were working a night shift. So I went 24 days without seeing the sun. That's a personal record. The case study project I'll show for this was located in a town called Kotzebue. There on the left, you can see the sunny tourist picture for Kotzebue. It's a nice town located on the ocean. It's about 550 miles straight line from Anchorage, and it's accessible by commercial flight from Anchorage there and back. So from a logistics perspective, not too difficult at all. And then lodging was in a local house that was serving as a camp for construction personnel. And the target was imaging gravel resources at a known gravel site. In these cities and towns that are distributed out on the tundra, gravel is a scarce and precious resource. So you need gravel in order to make roads to get around from house to house in time when it's thawed, and it's expensive and hard to get. So it's really needed for the infrastructure up here, but it's limited. Some towns don't go the gravel route and build boardwalks between house to house, but many places have a need for gravel, and most of these little villages have a runway, and you need gravel for a runway at a bare minimum. From an HSE perspective, sorry, I had that bolded on the next slide just to, from an HSE perspective, our concerns were the cold. So again, it wasn't extremely cold, but it was down to about -20 Fahrenheit at times during the project. I define extremely cold as less than, or well, I'll say -40. It gets really difficult to do anything at that temperature, or to do anything well at that temperature or below. And so traveling back and forth on snow machines and adding that extra wind, going 30-40 miles an hour on a snow machine to the project site, plus it being -20. Frostbite and hypothermia can be a real concern. So we're very careful to monitor each other and to dress appropriately and to keep all your skin covered. One of the crew on this particular project was an Iron Dog racer, which is a long distance snow machine race here in Alaska. So he gave me a lot of tips about how to make sure you don't get frostbite in those conditions. So we use that instrument I was showing in a TR5 configuration, which is 5 receivers and 1 transmitter, and then pulled multiple transects across each desired line in order to provide multiple depth levels of imaging down to about 45 feet below surface. The surface was snow covered. The vegetation, this is a late spring project. The vegetation Was cleared beforehand at a lot of cost of personal labor. So those guys are really hardworking to get out there and clear these lines. I was pretty amazed at their rate of clearing. And then the snow was light, fluffy Arctic snow, and it had a lot of it that year. If you stepped off the trail, so the construction crew also packed the trail with multiple passes on a snow machine. If you stepped off the trail, you would immediately sink it, up to your upper thighs, if not waist, in this light, fluffy snow. So collecting data without this preparation of the ground beforehand would be completely impossible for multiple reasons. Here's a picture of the resulting data. The data was really excellent quality. I'll show in a subsequent slide some soil types that were associated with the very high resistivity values that you see in the near surface. This was a high ice content silt. And then gravel materials were associated with what I have as blue colors here, and sandy intrusions as the green, and then bedrock below that. We also collected GPR and borehole data at the same time, or on the same project, using 50 megahertz antennas mounted on a sled down those same transects. And the resulting data were really high quality and helped us confirm the depths that we were seeing in the OMAPper for the bedrock surface. And since we had all those transects from that figure that I showed you, I was able to take the GPR data and make a 3D surface out of that, which the mining people can use to help guide their efforts as they start mining this particular area of gravel, and hopefully know what to expect ahead of time, both from the sand intrusion perspective and from the depth of the resource that they might encounter. I can't resist showing the cores from the boreholes that were taken at this site, because I happen to be a bit of a soil geek maybe, and these just amazed me. So I've seen some different permafrost, and generally you have different materials, but kind of in this matrix that's all soil filled and frozen. But in this particular case, we had these this silt in the upper 12 to 15 feet, and in between these silt layers was very, very clear ice. So there was a lot of ice, and it was very clearly segregated from the silt. And I hadn't seen anything like that before. So I was pretty fascinated by seeing this particular kind of permafrost. There's always something new. Finally, I'll talk about electromagnetics. There's a wide range of methods that fall into this particular category. Obviously, we've talked about other electrical methods, GPR and resistivity. Time domain and frequency domain EM methods are also used to measure ground conductivity and resistivity. I've had good success with mapping contaminated sites and contaminant plumes with the EM31, which is the instrument that you see there in this picture on a beautiful tourist day. It seems like you only want to take pictures on those days anyway, because who wants to take pictures in 45-mile-an-hour driving rain, of wind with driving rain? So all your pictures end up looking like field work is good weather all the time. Anyway, so we can also use these tools for detecting buried metal, such as underground storage tanks, unexploded ordnance, or metallic debris. Both the EM31 and the EM61 can detect buried metal. I'll show the EM61 in the next slide. And they can detect both ferrous and non-ferrous metal, unlike magnetometers where only ferrous metal can be detected. The EM61 that I just mentioned has long been the standard for buried metallic debris surveys, and for a long time was the standard for the US Army Corps of Engineers unexploded ordnance surveys. It's rugged and portable, like many of these geophysical tools I've been discussing, and is very sensitive to buried metallic debris. The transmitter and receiving coil you can see there on the bottom attached to the wheel, and then there's another receiver coil on the top, and then have a GPS mounted on top of that. There's a big push in the near surface geophysical community to move towards drone technologies, which has its place for sure. And there's a developing, I think it's called the EM6 light, is a developing tool that's being tested for use in detecting buried metal from a drone, and there's drone carried magnetometers as well. You might note as I'm talking that the picture on the right does not look like Alaska, and you would be correct. This was a Hawaii project. Some people were jealous, oh, you're going to Hawaii, but I despise heat and I despise crowds. So Oahu is not my idea of a terrific time, but nonetheless, it was a good project and has a different picture to show people. All right, so the final case study we'll talk about is EM61 surveying. This project was on a remote Aleutian island, about 1,400 miles straight line from Anchorage. I don't have it drawn, but we didn't get there in a straight line. Took a 3-hour commercial flight to a nearby town that's serviced by Alaska Airlines, and then a 24-hour boat ride on a landing craft, actually the landing craft that I showed in one of those first slides, to the island, and our lodging was that same landing craft for the duration of the project. The target was buried debris, and the primary concern here for HSE is it's a remote site. No bears on this island, but anything that happens to you from a health, safety, or medical perspective could be a very difficult situation to resolve when you're 1,400 miles away from Anchorage, where regular medical care is available. So a medic with a full stash of medic equipment traveled with us on this project and stayed with us on this project in order to be able to respond immediately if something bad were to happen to anyone. There is a runway on this particular island from World War II era, well, and after. Even though there was the possibility to evacuate someone if something should happen, you don't know what the weather's going to be like. So if you end up getting hurt and then there's an Aleutian storm for 5 days and you can't get a plane in, you're on your own. So having the medic there is essential, and even more essential is being extremely careful. So everyone watching out for everyone else and really having thorough HSE discussions each day to make sure that we try to get everyone through the project safely. I'll circle back to that discussion we had earlier, which is forgetting things is expensive. So I really feel this burden when I'm doing projects, and I worry pretty much ceaselessly about having everything that I need. If you, in best case, you can get something. For example, here, if the weather were good, you could get something, but that might involve a $20,000 to $30,000 charter flight. So that's going to be a big bullet to bite. And also, that's going to delay the project. So logistics is such an important part of what we do to make projects successful. Oh, I'll talk about the boat ride for a second too. I woke up in the middle of the night on the boat and thought, oh, I'm being tossed around a little bit more than I was before, actually a lot more. And I went outside and I was on the deck, or at least the second story of the boat. When we went down into the trough, the subsequent wave was up for me. I was looking up at it and I thought, well, that's interesting. And I went back to bed and we got there just fine. Here's some pictures during the good weather days. We did have some weather days that were 35 degrees Fahrenheit and pouring rain with 45-mile-an-hour winds. So those were also perfect hypothermia conditions. But we also had some great weather days for the pictures. You can see the EM61 in 2 different areas of the island. So really, the Aleutians are an amazing place. I really like working out there, and you really do feel the remoteness when you look around you, which is special. We positioned these data to survey grade quality using a base station from a known control point that was out there on the island. So that was that particular piece of the puzzle. And then also these data were processed on site on the landing craft immediately after acquisition, because the whole project team was out there. Getting there and back is too expensive to send people in pieces. So immediately after acquisition, I would process the data, and then the other project personnel could go investigate the findings. Here's a picture of the data results from one site. We were able to correlate several of these anomalies, 1, 2, 3 of them, with buried drums and go excavate those immediately while we were on site. So for a summary, there are many more near geophysical tools than I've talked about here, but I wanted to give a sampling of some of the work I've done in Alaska and kind of tried to cast a broad net as to different places that I've been within the state and different concerns from HSE to logistics that these different projects encountered. As I've talked about, which method is best for a particular project depends on many factors that might be hard to investigate beforehand, but nonetheless, we do our best to make sure we're going out with the correct tool for the job. And then every piece of the puzzle is essential and fun. So I really enjoy the logistics piece of it. It's I don't want to say lower level task because it's so important, but certainly there's very little math involved. But I have lots of checklists and I like checklists. And so I really enjoy the logistics and planning piece of it just as much as I do the geophysics. So again, I'll just reiterate, I feel really fortunate to be in this position to be conducting geophysics in the state of Alaska. I have one more thing to say, might be, well, anyway, since I have the stage and you all are listening to me, I just want to say that I really do feel honored to be part of this group of men and women that are solving some of humanity's challenges using geophysical methods. I would also like to say that I think as women, since I know this is a women's network meeting, that we really need to be careful to make sure that as we're trying to pursue equality, that we don't shift the pendulum to the other side. I've had the experience more than once of being in a women's group where in one particular case, the men who had come to that group to support the women, snide comments were actually made to them from the women, or been in women's conversations where similar things happen. I know it's risky to say this during a presentation maybe, but I would urge all of us to maintain professionalism and try to make sure that we stop the line ourselves at professionalism and dignity and respect for everyone involved, no matter the scenario. So yeah, I hope we can do that as we move forward as a geophysical community. Thank you all very much for listening, and with that, I'll take questions.
Well, I just want to say I agree with that wholeheartedly. So I agree with your 2 cents perfectly.
Okay.
That was a great presentation. We've got so many people saying what a great presentation this was. And we have a lot of questions, so I'm going to try and get through some.
Thanks, Bob. I'm going to grab my other water bottle because my throat is so dry.
One of the first things I wanted to ask that I saw in here, who are your clients for a lot of these projects?
A whole range. So oil and gas companies, and engineering firms in Anchorage, environmental firms in and outside the state. There's outside states doing a project here, and that runs the whole range from, bigger environmental engineering companies like a Jacobs to small local environmental engineering companies, construction companies. I was a construction company that was doing the work there, and COTS. And then, I even do projects for residential people who need to find an underground storage tank. So I really see a lot of the Anchorage business community and work for a whole wide range of clients. And I think that's part of the fun is meeting different people. And I really enjoy working with different crews up here.
And I also noticed that you have an amazing collection of equipment. And so I was kind of wondering if you have any resources or where do the funds come from? If someone wants to start a business doing this kind of stuff, like where can they reach out to get money to get equipment?
Right. Well, I was fortunate, I was pretty far along in my age, I guess, when I just made the leap to try to start a business. And so I had funds. So I put, I won't say how much, but tens and tens of thousands of dollars on the table of my own money to start the business, which is terrifying, but it's all worked out great. So I started with just the 2 basic GPR setups. And then I have a whole range of GPR from a gigahertz to 50 megahertz now. So I've added pieces along the way as projects came up. And then I bought the EM61 a year or so in. That's been very handy to have on site. And then for the resistivity and the seismic, I've pretty much rented those on a project by project basis. And just now, with this past summer, I felt like I have, it's a business decision. I felt like I have enough seismic business to justify spending tens and tens of thousands of dollars on a seismic system. So I'm pretty excited to get that. It should be shipping next week. Yay.
There you go, I'm muting myself. And actually there was a seismic question related to that, so I want to get down here. I'm interested to hear about your experience in collecting MASW or seismic refraction data in permafrost areas. Interested in knowing typical velocities observed and any field difficulties encountered.
I think, let's see, I've done a couple permafrost projects. Most of the seismic projects that I've had have not been in permafrost. So I'll have to get back to you about the specific velocities that I've encountered. I think one of the difficulties in permafrost is that it can also often be very close to the surface. So for using a Betsy gun source, for example, augering out and getting the source below the frozen surface can be difficult. And then from a refraction perspective, the velocity contrast might be lower in these frozen materials between a frozen material and the bedrock, and so might be less able to differentiate those materials from that perspective. I do like MASW. You're not running into that, for refraction, you have to have a positive velocity contrast, but that's not the case for MASW. So oftentimes that tool can do a better job in some of these environments.
Thank you. And now a question about the resistivity method. They say, I see it can be used for environmental mapping, including hydrocarbons. I'm assuming the goal is to map the extent of underground spills, but how about also looking at concentration levels and how accurate is it?
Yeah, so I think hydrocarbons in particular and mapping contamination, it's definitely a difficult target because you might often be looking at a low contrast between that contaminant and the background material. And also for hydrocarbons in particular, you might run into a situation where there's no contrast. So fresh hydrocarbon spills are very resistive, so you might have a more resistive material than the background resistivity of the water, the soil water. And aged hydrocarbon spills tend to be much more conductive. The microbial byproducts or the byproducts of microbial degradation of those contaminants tend to be conductive. So there might be somewhere in between where you actually don't have any contrast. And certainly the concentration is a big factor too. So I've had good success with the GPR and the EM61 at contaminated sites up here that were kind of tricky, but I've also seen the method not work. And I don't yet have a good data set, I want to, on concentration. So I get asked the concentration question a lot. And I don't have a good quantified answer for, at what concentration will this work? Because oftentimes there has been sampling ahead of time, or there was sampling and now they might want to add geophysics to the mix. And so they might have information about the concentration. Well, we have this concentration, will it work? But that's a tricky question. So I'm hoping to do more projects where I can build a database of information about where I've seen it work and where I haven't seen it work. I really am, I don't know if passionate, maybe passionate is too severe a word, but I really am interested strongly in contaminated sites and applying geophysical methods to them. So if anyone wants to talk more about that offline or see some other examples, I'm happy to chat about that.
Yeah, and remember the link to her website is just on the bottom of the screen here and her contact information. Just pointing that out real fast. A question, your career sounds like a lot of field work. Is your day-to-day a lot of time in the field, or is it a balance of office processing interpretation?
Well, yeah, good question. Thanks for the question. I think time-wise, it breaks down to about 50-50. And I really enjoy that because I really don't think I could handle a job where I'm in the office all the time, and kudos to you, those of you that are doing that and enjoying that. But I really enjoy the mix. I think if I were in the field all the time, I would also get burned out. But I really enjoy the mix. But as for an actual schedule, there is no schedule in my life. I run whenever there's a project available and try to do the best job possible. And sometimes in busy season, I'll collect data all day, and then I'll be working on someone else's report and someone else's data, not all night because I need sleep too, but a large portion of the night, and answering client emails at the same time, and then getting ready for the next day and sending out the daily reports, and then rinse and repeat, because people want results really quickly. Actually, for the first time, I had someone on a recent project ask for a result before I even started data collection. I told him he won a new award. But people often ask, right away, like, so I think that's an important part of being a consultant, is getting results, good results, but as quickly as possible. And so I often, just want to, actually, I don't want to leave things till the winter time when I'm less busy. I want to get results out as soon as possible. So there's definitely times when I am quite busy.
There you go. Yeah, I have the same issue. I'll collect miles, just so much data, and they want to turn around like 2 days later. I'm like, that's just not possible. So I know exactly what you mean. But following up on that, so what would be your #1 suggestion for emerging professionals and new grads that would like to build a career as a field geophysicist?
I don't know off the top of my head. My #1 suggestion: get experience, be enthusiastic. Enthusiasm can't make up for lack of experience, but certainly I think people want to work around people who are happy. So, be happy even if it's raining. I try to be happy when it's raining, or even when I'm not actually happy. Yeah, and try to find some place where you can work with people who can impart their expertise to you, and where you can build that experience. I think that was a problem I had coming out of grad school. I had field projects, great field projects under my belt, but there's a lot I didn't know, and a lot of field work that I hadn't done, different types of field work that I'm doing now. So I think you have to find a place to go get that experience. For a perspective of someone who's still in grad school, I would say try to be as diverse as possible. So somehow I recognized that a little bit during grad school. Probably my advisor, who was awesome, helped me, as he helped me with everything. But I did a lot of GPR, but also some electrical methods, and then also probably a third of seismic methods. So I was trying to diversify even then, to not, also because I didn't want people to pigeonhole me into, oh, she only does GPR, but also because I'm interested in all the methods, and I want to, be a diverse geophysicist. And it's easy to get stuck in what you know well. So if you just do GPR during your PhD, maybe that's what you'll just want to do. But I think being diverse is important. Sorry, I don't have a better answer.
Oh, here, I agree. Yeah, I agree.
Cool.
So I'm trying to kind of get different types of questions here. So what would you suggest as a basic kit for GPR if someone wanted to start up a GPR company for environmental studies?
Well, I guess that depends on what your targets are. So you have to think about that carefully. What depth do you want to image? And that's related to what frequency you choose. So your basic kit should include the depth range that most of your targets will be in. So my first kit included 500 megahertz antennas for shallowly buried utilities, and then 200 megahertz antennas. I can usually get 12, 14, even 18 feet or more in permafrost with those antennas. So that gives me kind of a good flexibility and depth range. And I think that's important. And I do have opinions about specific GPR equipment. GPR is my first love, I guess. So if that particular, but I don't, it's a professional forum. If that particular person wants to reach out, I'm happy to share some of my other comments about different types and different types of equipment.
Thank you. I have a couple of questions related to the gravels that you were looking at. So I didn't realize gravel can be a resource for your talk today. Thanks for your talk. So very curious whether the gravel is of high resistivity or low resistivity, because I understand that gravel itself is highly resistive, but its pores are usually filled with water. And here in Alaska, maybe it's filled with ice. So just not sure how to distinguish it when looking at like GPR or other things. Yeah,
that's a great question. And the answer is it's both. So I have seen both gravels that were more resistive than the background other materials, and gravels that were less resistive than the background materials. And of course, as that person mentioned, we have frozen and thawed gravels in the mix as well. And so gravel is a precious resource, but it's also a very difficult target. I like to be able to throw GPR and resistivity at it, but you must have data, because otherwise you really don't know unless you have some borehole data where you can say, okay, at this point, I'm seeing this resistivity and I'm getting gravel from this depth level to this depth level. I won't do a gravel project unless the client has also agreed to collect borehole data, just because I don't feel like it's worthwhile, because you don't know ahead of time. At least in my experience in Alaska, maybe it's different, and I'm sure it's different in other places.
And then John Bradford has a question. I'm going to say this word wrong. Did the gravels you imaged using resistivity host a talic, so unfrozen water contained within the permafrost?
In one case, hi John. For those of you who don't know, John Bradford's my PhD advisor. So thanks for listening today. In one case they did, in the Kotzebue work, there was a talic there in one location. And in most of the other resistivity imaging that I've done, we haven't encountered talics, but that is a target that clients are often interested in imaging, as either talics or mass ice, from an engineering perspective, and for what they might encounter when they're mining the resource. And so resistivity can do a good job, as you know, at both of those targets as well.
All right, we are out of time. I know there's still several questions that didn't get a chance to be answered, so please, if you you can email her directly with your questions to follow up. And seriously, wonderful presentation. Thank you so much for this today. This was a whole new learning experience for me, and I do some of this work, right? So I really appreciate your time. Thank you.
Thanks, Blair, and thanks everyone for attending. I really appreciate your time as well, and I love talking about geophysics up here, so thanks for the opportunity.
This is recorded, so it'll be up on the Women's Network page for viewing afterwards.
Cool.